So, anybody have any questions? Midterm exam 2 will be held on November 6th. It will be a take-home. It will be due on Monday, right before class.
What? Can we vote on it?
You can certainly vote on it. There's only one option on the ballot. This is how we do the election in Mother Russia.
Where do you have it that again?
On November 6th. Friday, November 6th. It will cover up through Lab 7. It will not cover table-based scheduling or real-time scheduling, which is what we're talking about next after table-based scheduling. I'm leaving town this afternoon. I will not be having office hours today. And Rohit will be lecturing on Friday. Feel free to bombard him with any questions you like. He has great stories, as you all know. The lab go okay? Did you get the lab done? Get the optimization all optimized and not pushing too much junk on the stack and so forth? So if I give you a radically different context switch implementation, you can draw stack frames for it and modify it and optimize it. If I make you have your bootloader code do a context switch, you'd be good with that. If I have you implement a multi-threaded printf. Isn't there all kinds of fun things we can do in this class? You guys can do more than you know that you can. Oftentimes you learn that on exams. So, I guess you taught me, well, Dr. Eames, no, we can't. Anyway. Hey, I'm there for you. So, anyway. Now that you have that little piece of information, any questions? Why? Because I want you to have a very rewarding and satisfying career writing embedded software. I want you to be prepared for industry. I want you to make gazillions of dollars. And in 6 months after you don't have to do labs anymore, you'll call me up or you'll email me and say, you know what? I hate to admit it, but the class was worth it. Okay, so if you remember what we were talking about, and I totally don't expect you guys to admit that it's worthwhile right now. That's too much to ask. Okay, so if you remember, we were talking about table-based scheduling and how we need to have deterministic processing in embedded systems. Non-determinism is evil. We hate it. We don't like it. We sometimes have to tolerate it, but nevertheless, we try to eliminate it where possible. So a large source of non-determinism in our execution in our current operating system we're building is in the priority queue. So the idea is we want to build a deterministic priority queue so that we can have our scheduler run in a somewhat deterministic fashion. The way that we're doing this deterministic priority queue is we're implementing lookup tables. So we are doing def by lookup table. We have this array that we call B that is an array of 8-bit values, 1 bit per process. So again, we think about it like this, where we just have 64 individual bits, or we kind of think about this as 64 slots where we can mark whether or not a process is ready. But this truly is 8-bit numbers. Okay? So We also have what we refer to as a summary register, or a summary word, 8 bits of summary, where each bit of this 8-bit word represents a mod 2 sum of one row of the B array. Okay? So if you just OR all the bits of one row of the B array, the corresponding entry in the A register will reflect that 1-bit sum. Okay? So row 7 in B is summarized by bit 7 in A. Row 3 in B is summarized by bit 3 in A. So where a bit is asserted in A, that corresponds to, or what that means is that there is a corresponding bit asserted in that row in B. So now the question becomes, how do we determine what's the highest priority ready process under the assumption that this priority table here represents the ready queue? What we decided is we need to be able to determine what's the rightmost asserted bit, or what's the index of the rightmost asserted bit of an 8-bit word. Okay? We decided we don't like to try to figure out what's the rightmost asserted bit of a 32-bit word if we're going to use a lookup table. The reason why is because we need to have a lookup table that's huge. If we can just, if we can scale down what we're trying to look at to be, if we have an 8-bit number and we want to figure out what's the index of the rightmost asserted bit, then our table only has to have 256 entries. So we defined BitTab as a table that has 256 entries, 1 entry per every type of combination of bits of an 8-bit word. So it has 1 entry for every possible value you can assign to an 8-bit word, and it tells you what's the index of the rightmost asserted bit in that word. It's kind of like a lookup table for implementing a log2. The first entry at slot 0 is a -1, because what that indicates is that there are no entries that are asserted in your word, and we don't care about that. So slot 1 is a 0, meaning that bit index 0 is asserted if the number is a 1. So you use the number that you're looking up as the index into the table. The table tells you what is the index of the rightmost asserted bit. So BitTab sub A, if you take A and you dump it into BitTab, BitTab sub A evaluates to, or returns, or gives you what's the row inside B where there is an asserted, or where that indicates there's a ready process. Not only that, it doesn't tell you just any row, it tells you what's the row with the lowest index. Okay? So if BitTab sub A says 3, what that means is that row 3 in B has the highest priority ready process. Which element in B sub 3 is it? Or which process indicated by B sub 3? Well, if we put B sub 3 into BitTab, that tells us what's the index of the process relative to that 8-bit number that corresponds to the highest priority ready process. So if B sub 3, it represents the priorities 24 to 31. If BitTab sub B sub 3 returns 1, that means that the bit position 1 in B sub 3 is asserted. So that means if bit position 0 is process 24, bit position 1 corresponds to 25. So in order to do the lookup, what I do is I calculate what's the offset into this table, and I use that to calculate how many rows am I skipping, and then what's the offset in the row that I'm currently calculating in order to calculate what the priority of the process is currently ready. So I figure out what the index is by dropping A into BitTab, and then I use that index to calculate a PID by dropping B sub ind into BitTab. That tells me what's the offset within the right row of B of the highest priority ready process. Then I figure out what its priority number is by taking that same index, multiplying it by 8, and then adding it to that offset. So you kind of think about this as it's the same math involved in calculating the address of a two-dimensional array, of an element inside a two-dimensional array. So ind is the number of rows that we're skipping over. There's 8 processes per row that we're skipping over, and then this tells us how many processes we're skipping over until we get to the right process within the row that we're accessing. So BitTab sub B sub ind, this tells us skip over from process 0, get to process 1, add that to the 24 processes that we've skipped over already by taking 3 times 8, and that tells us 25. If we want to get to the pointer of the process that we're after, we drop that PID into the all processes array, and that tells us what is the process that has highest priority that's currently ready. Okay? So that's death by lookup table for looking up the highest priority ready process. This is all great and all, but it doesn't work unless you can also insert processes into your ready table and remove processes from your ready table. So we have to look at insertion and removal. Well, before we do insertion and removal, is this okay? How many of y'all's heads are spinning? Anything I can do about it?
No.
Okay. So you can, your head is going to spin, and I'm sorry, it will. When you implement it, I hope that it'll make some more sense. Okay? But if there is something I can do about it, if you got some questions, I'd be happy to entertain. Whether my head can spin, you know. No? Okay. Yes, Mitch.
Wouldn't you want to, in our real implementation, check if whatever one of those has a -1, if it returns a -1, just an invalid something rather?
So in your implementation, would you actually want to check to see if you have any process that's ready before you do the actual lookup? Yeah, you would. And you can do that just by seeing if A, your summary register is 0. So if there is a process, or what you would really do is hide that behind a function call, which is going to be FIFO count. So if you say FIFO count, if FIFO count equals 0, skip it. Otherwise, give me the highest priority ready process, and the give me the highest priority ready process is going to be the code that does FIFO remove. So it's all buried behind your FIFO module.
So that -1 in the B array is never going to manifest itself?
It will manifest itself if your queue is empty. That's a flag so that you can determine whether or not your queue is empty. So it's important and it's there. You do have to deal with it. But if you've dealt with it properly, you're not going to access outside of the bounds of the arrays by virtue of the fact that your table returned you -1.
Okay.
Otherwise, you're not going to get a segmentation fault, although you're going to wish you had. Your board will just do weird things. And that's bad. Dereferencing invalid pointers or accessing outside of arrays makes your board, as I was saying to somebody this morning, that gives your board official permission to do random things. And the bugs manifest themselves in very weird ways. If your board is just doing, I cannot explain what, go and look at your FIFO implementation, make sure you're not dereferencing garbage pointers. Or insert printfs in random locations. One of those two. All right, so how do you insert a value into your table? Okay, there's 2 things we've got to do. We've got to update the entry for the corresponding process's priority in B. So each process has a bit in B. So if we're going to mark that process as ready, we've got to find that process's priority, or that process's corresponding bit in B, and mark it as a 1. And then we also have to check to see whether or not we need to update A. If we need to update A, we've got to mark A's bit that corresponds to the process's row as being a 1. It may already be a 1 under the assumption that some other process within that process's row is also ready, but we need to make sure that A reflects accurately what B state is. Okay, so the first thing we have to do is which entry in B does the priority PRI, this is not Public Radio International, any all NPR fans? Oh, come on. Y'all are college students. How can you not listen to public radio? Anyway, okay. Too busy with a PlayStation. Okay, so PRI is the priority of the process that we're trying to access, okay, or that we're trying to say is ready. So which entry in B corresponds to this priority we're after? So we can calculate this, or we can determine this 2 ways. Either we can calculate what is the entry in B, where in B do we update, or we use a lookup table. Take a wild guess what we're going to end up using. Def by lookup table. I'm going to first show you how to calculate it. Okay. So let's suppose that the priority of the process that we're looking at is priority 0. In binary, that's 0, 0, 0. Which index in B corresponds to, so when we say index, what we're looking for is, you remember, B is an array of 8 values. Which of those 8 ones contains the bit that we need to update for this process? Okay? So in our process 0, its priority falls on the first 8 bits. Right? So the first 8 bits covers processes 0 through 7. So that's why we're saying the index in B is 0. So we're going to update B sub 0 in order to mark process 0 as ready. Process 1, likewise, is in B sub 0. We're not yet saying which bit inside that 8-bit word we're after. We're just saying which of the 8 words inside B are we going to update. So this represents the index of the B array that we're going to grab when we're going to do an update. So 0, 1, 2, up to 7 all correspond to B sub 0. 8, 9, up to 15 all correspond to B sub 1. 16 and so forth correspond to B sub 2. And so we just go on like that. Okay, can you pick out a pattern here? So if you look at 0, okay, there's not much help here. 0 in binary, we get 0. 1 is 1, 0. So if we just read off the bits from right to left, 1, 0, 0, 0, 0, 0, 0, 0. 2, 0, 1, 0. Everything else above that's 0. 7, 1, 1, 1. Everything above it is 0. All those numbers are 0. 8, you have a 1 here, followed by zeros. Everything above the 1 is zeros. Up through 15, you have a 1 in bit position 3. Everything to the right changes. Everything to the left is zeros. Okay? What happens if we shift this guy to the right 3 bits? So if you take your priority number, shift it to the right by 3 bits, you end up with zeros in 0 to 7, because all the bits above, all the bits at bit position 3 and above are all 0. Here at bit position 3, they're all 1s, and everything above it is 0. From 16 on down, if you mask off the lower 3 bits, you have a 2. So 1, 0. And you end up with 1, 1. And so forth. So basically how you calculate which index in B, you just shift your priority right by 3 bits. Or in other words, you do an integer division by 8. So if you have 56 divided by 8, that gives you 7. 57 divided by 8 gives you 7. 15 shifted by 3 gives you 1. Same thing. Okay? So this lookup table is calculated simply by taking the priority, shifting it to the right by 3 bits, or doing an integer division by 3 bits by the number 8. The same thing. So we're going to compose a table that we'll call sum tab, or summary table, that just enumerates the answers of every possible priority value that we have. And again, we're listing from priority 0 up to 63. So this guy has 64 entries. It goes 8 zeros, then 8 1s, then 8 2s, so forth up to 8 7s. Okay, so which entry in B do we update? We can determine which entry in B we update by dropping the priority of the process that we're saying is ready into the summary table. That gives us an index into B. Then we use that as the index of B to grab the 8-bit value that we're going to update. What do we update it with? How do we impact the bits of B? Now that we know which slot in B we're going to grab, what do we do with it? So, 2 options. Calculate it, or use a lookup table. So, in order to calculate this, the calculation effectively ends up being, so we did an integer division by 8 above. Here we do the mod by 8. Okay, so it's just those low 3 bits. Again, what we're doing is we're trying to figure out what's the index of the bit that we're going to update, assuming the priority is as listed here on the left. So for priority 0, we're going to update bit 0 in the word that we're accessing. For priority 1, that's bit 1. Priority 2 is bit 2, and so forth. Priority 8 is bit 0. Priority 9 is bit 1. Now, again, it's relative to the right 8-bit slot in B. So once we pick out the right slot in B, which bit index in that slot are we going to update? And that's what this bit offset tells us. And again, what you can do to calculate this is just the priority masking off every bit except for the last 3. You just grab the last 3 bits, and that's what those guys are. Okay? So we can compose a table called bit offset that just lists all these numbers in that rightmost row there, in that rightmost column. So bit offset goes 0, 1, 2 to 7, 0, 1, 2, 3, 4, 5, 6, 7, 0, 1, 2, 3, 4, 5, 6, 7. So now to do the update, you remember what we're doing is we're going to grab a particular word of B and we're going to write to it. So the word that we're going to write to it, we take a PRI, we dump that into the summary table. That gives us the index of B. We dump that index into B, and that grabs us the appropriate 8-bit value that we're going to update. We write to that value. What do? We're doing an OR equal. So we're going to take that value, read it out, OR it with a value, and then write it back to that location. So what are we going to write to it? Well, we've got to write to a particular bit location. Which bit location are we going to write to? We take PRI, drop it into the bit offset array. That tells us how many bits over we're going to access. And we shift a 1 over by that much and OR it into the number that we're going to access. Okay? So this says 1 shifted by the bit offset that we calculate with this bit offset array here. Okay? So 1 shifted left by bit offset sub PRI. That gives us a mask that we're going to update our B array slot with. Well, if we're using a lookup table for bit offset and we're doing a shift, why don't we just pre-compute the shift? So we can pre-compute the shift and make yet another lookup table. So we can define mask tab. Mask tab is the same thing as what we were saying before, but shifted. So where we had 0, 1, 2, 3, 4, 5, 6, 7, now we have 1 shifted by that amount. 1 shifted by 0 is 1. Then 1 shifted by 1 is 2. 1 shifted by 2 is 4. 1 shifted by 3 is 8. And so forth, up to 128. So 1, 2, 4, up. These are just the powers of 2. Okay. So now, for doing our update, what we can do is we say, take our PRI, pick out the right value of B, we OR it with mask tab sub PRI. We're going in the right direction here. We're actually reducing the number of table lookups by 1 with this one. So we just have this mask tab sub PRI. So that tells us what is the mask that we want to use to update the particular bit inside B that represents the process indicated by PRI. Okay, now that we've updated B, we also need to update the summary register. How do we update the summary register? Or why am I updating the summary register? If I set a bit in B sub 3, that means I need to assert bit 3 in the summary register. So, which bit I assert in the summary register corresponds to which index in B I did the update for. So if B's index that I updated was 0, the mask for A that I'm going to use to update A is going to be a 1 because I want to update bit 0. Okay? So I want a 1 in the bit 0 position. So that gives me the value 1. If B's index is a 1, then I want to update A using a mask that writes to bit position 1. So that mask is a 1, 0, or the number 2 in base 10. Down here for 7, I want to update bit 7, so I put a 1 in the MSB position. That's 128. So the different indices of B that I use correspond to these different masks. So 1, 2, 4, 8. This is just the same thing that I had in my mask table. Okay? So when I want to update A, I take the current value of A and I OR it with taking my PRI, dumping it into the summary table. That gives me what index in B am I updating. And then I take that index and drop that into the mask tab. That tells me what is the mask. And then I just OR A with that mask. So what that'll do is it'll update the right position in A, indicating that this priority band has a ready process. And note, I do this regardless of whether that bit's already set in A. It might already be set. I don't care. I don't want to have to stop and do an if statement. I just OR it with the 1. If it's already a 1, 1 OR with 1 is still 1. Okay. So summarizing, when you're inserting, you need to update B, then you update A. You just use these lookup tables to update B and update A. Now, how do you remove? If you want to remove something from the lookup table, you do the same thing as insert, but do it backwards. Instead of ORing it with the mask, you AND it with the bitwise complement of the mask. And that way it'll just zero out the right, the particular correct bit in the summary register or in the right B 8-bit value. Okay, so the whole point about this is you're going to take your priority queue module and implement it with tables. You're going to use these tables for both your ready queue and your blocked queues. So then your interface to the priority queue module shouldn't change too much. You may want to change it, and it's okay if you do, but for the most part, if you've implemented modularity correctly, you shouldn't have to change too much about it. Okay. The other note that I want to make note of is that you can choose with this approach to have your current running process marked as ready. You can have its corresponding bit position in your table as a 1. Or you can choose it to have it be not ready because it's running, and the process isn't running and ready at the same time. I'll tell you at this point, it's convenient and makes it a little bit easier, Lab 9, if you have your process that's running be also marked as ready in your table. Okay? When we do priority inheritance, priority inversion, and the priority ceiling protocol semaphores, this makes life just a little bit easier. If you want to not do this, that's totally fine. I've seen plenty of people do it the other way, and that works. But what I'm telling you now is that if you mark your process that's running as ready, and he's resident in your ready queue, then it makes life a little bit easier later on. Not a ton, but enough that if you want to make note of it, by all means, that's probably a wise idea. Okay, so that's the first part. I won't say first half, but that's the first part of Lab 8. You got to implement this ready table stuff. Questions on it? So looking forward to that. Deterministic priority queues. Death by lookup table. Okay. What we talk about next is where life gets officially really, really ridiculously cool. As if it weren't already. So, okay. I've mentioned you might want to read the book every now and again. This time I mean it. Okay, chapter 13. This is what separates real-time systems from desktop processing systems. Doesn't necessarily make desktop processing systems bad or real-time systems good. It's just why we have a separate class for a real-time system as opposed to a desktop operating system. The idea is we want to be able to schedule a set of tasks, and we want to prove that it's going to work. How do we prove things? Well, this goes back to when you've taken all your math classes. We know how to mathematically prove things. We have to set up a situation to where we can apply mathematics that will govern the behavior of the system. And we have to manipulate those mathematics to the point to where we can achieve a proof, where we can know what the system's going to do before it actually does it. This is something that's all too uncommon in software development. We hack code, we test it, we make sure it works, we declare victory, we move on. Well, testing is not a proof. Can you prove that your system is not going to cause your airplane to crash? Can you prove that your elevator is not going to get stuck? Can you prove that your Mars rover is not going to get stuck on a rock because you've implemented your semaphores incorrectly? Which is what happened in 1997 with the Sojourner. Got stuck on a rock because of a priority inversion problem, which is something I'm going to teach you about in this class, how to do priority inversion or how to not do priority inversion and how to avoid it. Okay? So real-time scheduling is a theoretical approach to how to model software and prove that it's going to do what you want it to do. This first set of slides, I call it real-time scheduling or real-time scheduling 1. We're going to introduce a set of assumptions that are very limiting, that you can't really use in real systems, because what we're doing is we're going to establish a basic model that we can start to talk about how to do math for real-time system analysis. Okay? And there's a ton of theory. Textbooks, complete textbooks have been written just on scheduling and schedulability analysis. Okay, some of them very heavy on the math. So in this class, we're going to give you a good introduction to real-time scheduling analysis and schedulability theory, but we're not going to get into the depths of all of the things that have to do with scheduling and schedulability analysis. The reason why is because we just don't have time to do it. I don't know that we necessarily have the willpower to do it on top of the labs anyway. But we're going to do enough to scratch the surface and give you some tools in your tool belt so you can look at this later. Okay? So real-time scheduling is how do we deal with math in order to prove that our system works? And specifically with respect to timing deadlines, how do we prove that our system will work in a timely fashion such that our timing deadlines will be met? In order to even talk about that, we have to formalize the notion of timing deadlines. So, a little bit of scheduling theory, then we'll deal with implementation. Okay. A few assumptions, a whole bunch of assumptions. We'll start to relax these assumptions as we go on, but just for the sake of initializing the discussion, we first say that we have an application, and we have an application that consists of a fixed set of processes. By fixed set of processes, we're not going to consider for the time being that we can dynamically add processes. Okay, so we know about all the processes right from the get-go. Okay, we're going to assume that all processes are periodic. By periodic, what we mean is that they're going to wake up every so often. Okay, and what that means is that they are not going to want the CPU 100% of the time. So they're going to do their business, they're going to be released, and then they are going to, at some later point, be released again. During the times in which they are released, they're going to be doing some work. Okay? So processes are periodic, and not only that, but they are fixed. They have fixed periods. So when the processes are re-invoked, the time between invocations is a fixed time for each process, and that's assigned by the user beforehand. And the period of a process doesn't change over its lifetime. So a process gets invoked, it gets released, it has to do its work. At some other time, it'll be released again. It has to do its work. At some other time, in the future, it'll be released again. The intervals in between which the processes are released is fixed and known when the system gets built. All right, processes are independent of each other. That means there's no data sharing going on. There are no critical sections in this initial framework. So process A does not synchronize with process B. There will be no disabling the interrupts. There will be no semaphores. There will be no data sharing. There will be no swapping data back and forth. So all processes, they do their own thing, and they're independent of each other. We're going to assume that our system overhead is negligible. So in other words, the scheduler time that you've just so painstakingly measured over the last day, maybe at 11:50 last night, we're going to assume that that's zero with respect to how long the processes take to run. And that's not necessarily an invalid assumption. Yes, the scheduler takes time. Yes, the context switching takes time. But if the time in which your processes are invoked and the time that they take to run is much, much larger than the system overhead, then the system overhead is just in the noise anyway, so we're just going to ignore it. Okay, so for the theory part of this, we're going to assume that context switching time, overhead time, interrupt latency, or interrupt overhead, all of that's ignorable. So the only time that gets taken up is the time that's taken by processing. Okay. Assumption number 5 is that when a process runs, it's got some fixed amount of work to do. So this kind of makes sense because when you run a process, it's got to do something, right? You're going to assign it some task to do. We're going to assume that the amount of work that a process does is fixed. Okay? We call this the worst case execution time, or WCET. So we benchmark a process and we figure out if it runs in isolation, it's going to do the same thing every time it runs, every time it gets released, and the amount of CPU time that it wants is the same every time that it runs. Okay? So if you're going to call printf and you're printfing the same thing every time, we're going to assume that that thing takes the same amount of time every time you run it. Okay? But obviously, we're not going to do printf because we don't share a critical section. So all processes have to perform some amount of work each time they're invoked. So a process lifetime goes, you invoke the process, it gets released, it is allowed to be scheduled. When it gets swapped in, it does its fixed amount of work, okay? When while it's doing its work, it could get swapped out, it can get swapped back in, but it has to complete a fixed amount of work before it can go to sleep. When it's done with its work, it goes to sleep. At some point later in the future, it gets released again, and it has to do that same fixed amount of work before it can go back to sleep. Okay. 6 is a big one. Each process has to complete its work before it gets invoked again. So what we're saying is that each process is periodic in the sense it gets released, and at some fixed point in time later, it gets released again. Right after it gets released, it's got to do its work. It might get preempted. When it's released, that doesn't necessarily mean it gets to access the CPU. When it gets released, what that means is it gets to proceed and attempt to access the CPU. If the scheduler decides to swap it in, great. It gets to access the CPU and starts to do the work that it's supposed to do. But it can only do work while it gets the CPU, while it's the running process. It can get swapped out in favor of some other process, assuming some other higher priority process gets to run. That higher priority process gets priority until it finishes its work. So you could get interrupted during the work that you're doing. So on a timeline, you could be implementing a little bit of your work, and then you have to wait, and then you implement a little bit more of your work, you have to wait, you can implement a little bit more of your work. But the whole point is, system correctness criteria is based on 6, where you have to do all of your work before you get released again. So if you're still busy working on the work that you were supposed to do when you were invoked before, when the time comes that you're supposed to be released again, we call that missing a deadline. So each process has a deadline. We're going to say that the deadline is, well, missing a deadline is bad, 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 bad. Mitch?
What exactly is the difference between being released and being scheduled?
Okay, so the difference between being released and being scheduled. In our system, when you are released, you're put on the ready queue. When you're scheduled, you're the running process. So you can have several processes that are ready, but only one of them is running.
So when you get preempted, you're saying you're not getting released?
So when you get preempted, you could when you're preempted, what it usually means is that there has been a higher priority process than you that wants the CPU. And so you get swapped out, and they get swapped in, and they get to run. And you get to wait until they're done. And as soon as they're done, assuming you're the next highest priority process, after they're done, you get to run. Okay? So you get released means you get put from a holding cell somewhere, you get put on the ready queue. And you get to compete with all the other processes that are ready and waiting for the CPU. If you're the highest priority ready process, you get to run.
And then when you're done with your work, you go back to some.
You go back to the holding cell. Okay. So
there's like another state.
No, it's the block state. The holding cell is you get blocked on a semaphore. But we're just using that as a mechanism to keep you from competing for the CPU. Because if all processes all the time are always competing for the CPU, then the highest priority process will get 100% of the CPU all the time. So the whole point is, what we're saying is not all processes want the CPU all the time. Otherwise, what are we doing here? Okay? So the highest priority process may want just a sliver of the CPU time, but it has to have access to the CPU at a regular interval. So when it runs, you want it to run, and you want it to get the CPU time immediately. So you release it, it gets its CPU time because it preempts everybody else, but it does its 2 microseconds worth of work and then goes back to sleep. And then the operating system will re-release it when it's time for that process to be released again. As soon as he's released, he gets access to the CPU because he's the highest priority process. Between the time where the highest priority process is sleeping and the time it gets released again, other processes can run. So during that time frame, the second highest priority process gets to win. And he gets to access the CPU, and then he'll go to sleep. And then during the time from that point to where the highest priority process is released again, you get some chunk of time where the third highest priority process gets to have access, and so forth. Okay, does that make sense? So what we have is just slots available, and the highest priority process that's available, that's waiting for the CPU, gets to run. you have a certain amount of work to do. That work is measured in units of time. It's not measured in an absolute timeline. It's just measured in how much time do I need the CPU. So only when you access the CPU do you get to eat CPU cycles. And do you get to count that against the work you've got to do. And you've got to finish the work that you've got to do before it's time for you to be released again. Okay. So every process has to finish its work before its deadline, and we will assume for now that the deadline of the process is equal to its period. So what that means is that you have to finish your work before you get released again. There are other models where we can assume that the deadline for a process is earlier than its release time, but for right now we're just going to say you have to finish your work before you get released again. Okay. We'll define some notation. C sub I. C sub I is the compute time, or the worst case execution time for process I. T sub I is the period for process I. So C sub I is the amount of time you have to be eating of the CPU's time in order to get your work done. T sub I is how much time elapses from one release time to the next release time. Okay, all processes are independent. Potentially, we could release all processes at the same time. If all processes in our system want to have the CPU at the same time, we refer to that as a critical instant. That's the worst case scenario. That's the hardest time to schedule everything. So we're going to refer to this as the critical instant, and we're going to devise a situation or a scenario in which we can schedule or prove that our system is schedulable under certain conditions at this critical instant. And if we can prove that it works for the critical instant, then we can say that it's not going to get any worse than this, and if we can make it work for our critical instant, it'll work for every other situation. Okay. So the question that we want to analyze is, can I guarantee schedulability? Is it possible to guarantee a situation where all the processes in my system, given their worst case execution times and their periods, will meet their deadline criteria? So will every process be able to satisfy its compute needs without exceeding its period? If we can prove that, then that means that our system is schedulable. Okay? So we need to be able to guarantee forever and always that we'll meet this deadline. Okay. One approach to real-time scheduling is defining a cyclic executive. So what this means is you're going to define, we also call it a static schedule. We want to be able to decide an order in which tasks should run, and you decide that order as you write the code. Okay? So what we're going to do is effectively write a loop that invokes tasks in the order in which you decide. So if you've got 10 tasks, A, B, C, D, and E, you might decide to run A, then B, then wait for a little bit, then run A, then B, then C, then wait for a little bit, then run A, then B, then D, and wait for a little bit, and so forth. In some situations, it's possible to plan out on paper before you even run your tasks which processes should run when. If you can do that, then this is the most efficient way of implementing an operating system because you have no operating system. You eliminate all system level overheads. So what you end up with is a cyclic executive that looks like this. So you say T equals T time, all T equals T time, you wait for a timer tick, and then you run a few processes. And these guys, the order in which they run is significant. So assuming you have the ability to run process A, then B, then C, and if you wait for a tick, then run A, then B, then D, then E, and then you repeat this whole thing, if you can cook this up and prove that this will make your deadlines be satisfied forever and always, this is great. All process invocations really just amount to function calls. You use a wait function to make sure you synchronize with the clock so that you release processes by invoking them in accordance with their periods. You have no preemption. You have no cooperative swapping. You have no context switch. You have no interrupt. All that you have is just a GLOPA C code that runs. If you can make this work, if your situation allows this, this is the right idea to do because you have no overheads. It's very, very efficient. Why don't you just do this then? Why have I been talking about context switching and scheduling and processes and all of this business? Why don't we just use cyclic executives? You can't always use a cyclic executive, and it's very difficult to tune a cyclic executive for different situations. So it's hard to make a correct cyclic executive. So And there are very common situations where you can't make a cyclic executive. For example, what if the period of a task is smaller than the worst case execution time of another? So what that means is you need to release task A 50 times within one given chunk of time, but task B takes up more than that chunk of time. So you have to be able to preempt task B. You have to be able to stop B's execution in the middle. With a cyclic executive, you can't really stop things in the middle. Sometimes there might be a way of organizing the code so that you can break task B up into multiple tasks, and that's a possibility. But typically, something like that would require preemption. Okay, so how can you guarantee preemptive scheduling? How can you use preemptive scheduling and still guarantee correctness? What we're going to do is talk about a piece of theory that was published by two guys called Lew and Leyland in 1973, and this is a seminal paper on real-time scheduling. And everybody refers to this. It's called rate monotonic analysis. And their theory is based on how much CPU time, or what percentage of the CPU time are you utilizing with the processes that you are implementing. Okay? So you can't use more CPU time than is available. So the idea is if you've got a process that its compute time is, if it has 10 units of compute time, or 10 seconds of compute time, and it needs to be released every 10 seconds, what that means is it's going to be released, it'll compute for 10 seconds, and then at the end of that 10 seconds, it's done, it goes to sleep, but immediately gets released again, and has to compute for another 10 seconds, it goes to sleep, but immediately gets released again. It's using 100% of the CPU time. If you add a second process to that even has a, let's suppose that second process wants to compute for 1 second and get released every 5 seconds. There's no room left. There's no open spot to schedule that second process. So such a situation is unschedulable. So the whole idea is we want to make sure that with our process model, we have to, first, we can guarantee that we are not schedulable if your processor is 100% utilized. So what we want to be able to do is come up with a theory that says, well, if we underutilize the processor, can we prove that if we underutilize it enough, that the system will be schedulable? How much CPU time does a particular process eat? If you take the ratio of its compute time to its period, this tells you what percentage of the CPU time that a particular process is going to use. Okay? So if you have process A that uses 3 units of time and has a period of 9, it has a 33% utilization. Here is the great thunder of the proof, or the thunder of the theorem that Lew and Leyland postulated. If you calculate the total utilization, which is the sum of the ratios of compute time to period of all the processes in your system, that's your utilization. If U is greater than 1, it's impossible to schedule on your given processor because you're trying to use more CPU time than is available. However, if you follow this criteria, if you calculate your utilization and it's less than or equal to n times the quantity 2 to the 1 on n minus 1, that's a guarantee of schedulability. So if you can meet this criteria, if you underutilize your CPU utilization, and treating this as an upper bound where n is the number of processes in your system, then this guarantees that your system will be schedulable according to if it follows all the assumptions that we've talked about today. Okay? So that is a necessary and sufficient condition, that is a sufficient but not necessary condition for schedulability. Anyway, we'll talk some more about that. Rohit will finish talking about this next time. Lab 7's posted. Enjoy.
I think they are on the computer.